Welcome to your very last day of learning something new in statistics. Woohoo! Okay, let's get us started. So, in chapters 9 and 10, we discussed inferences regarding a single population parameter, right? So we had mean or proportions. In this chapter, all we're going to focus on is we're going to look at proportions, but now of two different populations and comparing them. So we're basically doing our confidence intervals and hypothesis tests again. So it'll be good practice for us. So a sampling method is independent when the individuals in one sample do not dictate which individuals will be in the second sample, whereas the sampling method is dependent when the individuals in one sample determine the individuals in a second example. Often we call it a matched pairs. So let's go ahead and take a look at these examples and decide which one's which. Gillette Junior College decided to implement a course redesign of its developmental mathematics program. Students are either enrolled in a traditional lecture format course or a lab-based format, in which lectures and homework are done using video and the course management system MyMathLab. There were 1,200 students enrolled in the traditional format and 300 enrolled in the lab-based. The goal of the study was to examine whether the proportion of students who passed the lab-based format exceeded that of the lecture-based format. So here, the sampling method is independent because the individuals in the lecture format are not related to the individuals in the lab-based format. Whereas this next example says, do women tend to select a spouse who has a higher IQ than their own? To answer this researcher question, the researcher randomly selected 20 women and their husbands. They measured then the IQ of each husband-wife team to determine if there's a significant difference in IQ. These ones are dependent. The sampling method is dependent because once a wife is selected, right, her husband is also automatically enrolled in the study. Okay, so let's talk about your conditions. These conditions seem familiar because they're the same conditions for proportions of hypothesis testing of one proportion, right? So the samples are independently obtained using a simple random sample or a randomized experiment. Think about words like, hey, if it talked about like a survey or something too, we know that's going to be random. We know that our n times p times 1 minus p has to be greater than or equal to 10. The only thing here is you got to check it for both proportions you're looking at. So you have two separate samples we're going to check it for. And that these samples have to be less than 5% of the population. Okay. So these steps should seem familiar too. Determine your null and alternative hypothesis. So you'll notice we still have the equal to for all our null hypothesis, but this time we just compare the two proportions. We still have two tails, which is not equal to, a left tail is less than, and a right tail is greater than. Okay, we're going to use our technology to compute it. If you want to do it by hand, there's some formulas for you. I would not stress about those. Remember, if the p-value is less than alpha, reject the null hypothesis and conclude there is sufficient evidence to support the alternative. Whereas our p-value is greater than alpha, we fail to reject the null hypothesis and conclude there is insufficient evidence to support the null. Let's go ahead and do it then. Researchers at the Harrison Interactive wondered if there's a difference between males and females in regard to some common annoyances. They asked a random survey of males and females regarding this following question. Are you annoyed by people who repeatedly check their mobile phones while having an in-person conversation? Among the 415 males surveyed, 178 responded yes. Among the 560 females surveyed, 206 responded yes. Does this evidence suggest a higher proportion of females are annoyed by this behavior? Conduct your hypothesis test using alpha is equal to 0.05. Okay, so let's check our requirements. Simple random sample. The fact that they said, hey, this is a survey, we're assuming they're following a good technique, so it is a simple random sample. This next one with n times p times 1 minus p, we may want to take a look at. So let's talk about p of the men, the proportion of men. We have 178 out of 540 men. So what is that proportion? Let's see. 178 divided by 540 And we get, let's use 3 decimal places, 0.3, actually let's use 2, 33. Okay, so here if I do my 540n times p, which is 0.33, times 1 minus 0.33, we want to double check that that value is greater than or equal to 10. And sure enough, we get 123.82, which is greater than or equal to 10. Okay, we're safe there. Let's double check the same thing with women. So for women, we have 206 out of 560. Oh, you know what? Sorry, look at that. I typed in the wrong number there. You're gonna wanna make sure that's a 4. I don't think, no, still the wrong number. 540, not 460 or 560. Let's try that one last time. Third time's the charm. Okay, sorry, slightly different number, but still way bigger than 10. We get 119.39. Okay, now for women. 206 divided by 560. And we get 0.37. So 560 times 0.37 times 1 minus 0.37. Okay, let's try that. So we end up with 130.54, which is greater than or equal to 10. Okay, that condition's met. Then the last one we have is the less than 5% of the population. So sample is less than 5% of the population. I'm gonna go with on that one. We're gonna kind of assume that's true. 500 people for each men and women definitely seems like less than 5%. Okay, so now we're gonna go ahead and write a hypothesis. So the hypothesis starts off really similar to what we did before. P, and then we usually just label it like of men, or you can use P1 and P2 equals P of women. Our alternative though, so H1 or HA, we're going to leave P men and P women in the same spot. But we're saying a higher proportion of women. So the alligator should be eating the women. Okay, so now we're going to go ahead and do a test. So similar to our 1 proportion, we're now just doing a 2 proportion. 2 prop Z test. Okay. So here it asks you for X1 and N1. So whatever you put on the left, which in this case was our men, is what you got to put there. So we're going to have the 178 and the 540. And then your X2, N2 have to be then the women, whoever you have second. So just be careful here that you don't get things confused. You're putting things in the right spot. So we got 206 and we got 560. Okay, and then we're doing that P1 is smaller than P2 because we think that a higher proportion of women, oh look, it's already highlighted for us, are going to be that case. So here our test statistic is Z equals negative 1.33, and our p-value is that first p, so 0.092. Okay, now we're going to compare our p-value to our alpha. So since 0.092, this is actually greater than our alpha of 0.05. So since p is low, reject the hoe, p is not low here, we're going to fail to reject the null and conclude there is insufficient evidence that females are more annoyed than males by this behavior. Okay, let's do it again. Many high school students take the AP test in different subject areas. In 2007, of the 211,693 students who took the calculus AP exam, 1,598 of them were female and 1,995 of them were male. Is this enough evidence to show the proportion of female taking the calculus AB exam is different from the proportion of males taking the calculus AB exam? Okay. Check the requirements. So we want it to be like a simple random sample. In this case, I feel like it kind of depends on the way you're thinking about the sample, right? This almost seems like an entire population here, but maybe we're looking at like in comparison to like all years, like is this one year, maybe we just randomly selected it. That's kind of more what I would think about in this case is like, hey, this 1 year, how does it compare to all the other years? So choosing this 1 year, think about it as like a cluster sample, right? We took everyone in that 1 year, makes that a simple random sample. Okay, as far as checking your requirements, we got two populations. We got the males, and we got the females, the proportion of males and proportion of females. The strange thing in this case is we're going to take the 102,598 out of the 211,693 in both cases. So as we divide these two numbers, 102,598 divided by 211,693, we end up with 0.48, which means the females should be the other proportion of that, so like 0.52, but let's just double check. 109,095 divided by 211,693. Sure enough, that is. So as we do our sample size, which is 211,693 times 48 times 1 minus 48, we end up with a number that is well over 10. The other one will actually give us the same number. I don't know if you realize this, but like think about when we do 211,693, we're doing 0.52. And when you do 1 minus the 0.52, that's the 0.48. So you end up with actually the same result. The 52,838, 0.57 is greater than or equal to 10. Last but not least, we have to assume sample size is less than 5% of population. And I'm kind of considering in this case the population of all AB Calc testers ever. So not just in that 1 year. Okay. Our hypothesis then is we're comparing the proportion of men and women again. So we think the men and the proportion of men and women are going to be the same. An alternative is we just say that they're different. The fact that we're just saying they're different, I don't care who's higher than who, we just want them to not be equal to each other. So it's going to be a two-tailed test. So now let's go ahead and perform the test. So we're doing our 2-prop z test. Okay, we put men again first, so we're going to have to put all the men number first. So the men numbers are 102, 598, and then the 211, 693. Okay. 102. Oh, 102. Oh no, I messed up. 109. I think I did those wrong. I mixed these up here. Okay, everyone pay attention. I swapped these by accident. It's okay, it hasn't impacted anything yet, but the females, this was the females, and this was the males. Okay, so based on the way we wrote it, we actually need to switch these. And we're going to have to use the larger number first, the 109095. Close call there. And then here, the 211, 693, and N2 is going to be 102, 598 for women. And then your N is still the same size. And then we are choosing that they're a difference, they're not equal to. Okay, this p-value is ridiculously small, right? So our p in this case, we get 1.09 e to the negative 88 is in essence 0, right? Because that's saying that there's 78 zeros before that one. This number is 19, or almost 20 standard deviations away from the mean. So with that being said, since 0 is less than 0.05, which is our alpha for 5%, we reject the null and conclude there is sufficient evidence to say the proportion of males and females who take Calc AB is different. So this is one of those cases that, remember, we used a really large sample size. So with that being said, you know, we may want to consider, for example, that, hey, you know, 48 to 52% is really not that big of a difference. This may be one of those cases where we got a statistically significant result, but it's not practically significant. Okay, one last one. Confidence intervals. A confidence interval is the difference between two proportions, right, of independent samples. So remember, this time we're going to have our point estimate, but your point estimate is going to be the difference between your two proportions. That's going to be kind of center. And then we're going to add or subtract. So this is still your point estimate. And then we're going to add or subtract some, right, we call it like margin of error. And our calculator will figure out those things for us, but I just want to kind of point out to you what's happening. Our conditions are the same as we've been using before, right? Your samples were obtained independently using a simple random sample. We want these, our n times p times 1 minus p, to be greater than or equal to 10. And our sample sizes are no larger than 5% of the population. And remember, we're estimating here now, we're blank percent confident that the difference in proportions of whatever the situation is between these two bounds. Okay, so let's go ahead and do a confidence interval or two. In the Sullivan Statistics Survey, 695 out of 1,000 randomly selected males had a Facebook account, and 845 out of 1,000 randomly selected females had a Facebook account. Construct a 90% confidence interval. So notice, hey, we got the simple random sample. We could check that condition about n times p times 1 minus p is greater than or equal to 10. And we could say here as well that, the 1,000 people is probably less than 5% of the population. Okay. So now let's go ahead and take a look. So we're going to go to our tests. And remember, for confidence intervals for proportions, we went all the way down here. So rather than just doing a 1 prop z interval, we're going to do a 2 prop. Okay. So the first thing they ask you is for the N1 and X1 and M1. So you got to decide. In this case, since I put males first, we're going to want to do males first as well. So in our males, we had 695 out of 1,000. For our females, we have 845 out of 1,000. And our confidence level is 90%. So we're going to use 0.90. We're going to go ahead and hit calculate. So what we got here as a result is we got negative 0.1805 and negative 0.1195. The reason why it's negative is the proportion for females is greater than the proportion for males. So we could say, hey, we're 90% confident that the difference between proportion of males and females who have Facebooks is between negative 0.18, I'm going to be a little lazy and use two decimal places, and negative 0.12. Or another way to interpret this would be, hey, there's 90% confidence the difference of proportions is in the interval, right? In this case, I could say in the interval, negative 0.18 and negative 0.12. So we can conclude that women are at least, right? Because we're more than 10%. It's negative because the women have the greater value. At least 10% more likely to have Facebook accounts than males, right? It's really between a 12 and 18%. That difference is between 12 and 18%. Let's talk about proportions here. Okay, let's do one more. The number of Prius owners in a random sample is 500 Californians is 50. The number of Prius owners in a random sample of 1,000 ions is 25. Create a 95% confidence interval in the proportion of Californians and Iowans that own Priuses. So here the way that it's kind of phrased, I probably do the proportion of Cali and then minus the proportion of Iowa. Okay, so stat, go right to your tests. We're going to go to your 2 prop Z interval. So we're going to start with California. So 50 out of 500 versus Iowa is 25 out of 1,000. Our confidence level is 95%, so we're doing 0.95. Always a good idea to write down what your inputs were, right? This is you showing your work. Okay, let's go ahead and see what our results are. So as we hit calculate, we end up with an interval of 0.04, and 0.103. Okay, so there is a 90% confidence the difference in proportions of Prius owners from California to Iowa Sorry, it's having a little difficulty here. California to Iowa is in the interval 0.047 to 0.103. So we can conclude that because we put California first, that they are more likely. Californians are more likely to own a Prius than Iowans. I'm going to let you guys go ahead and finish that. Okay, so that wraps it up. This is the very last thing we're learning. So go ahead. You've got homework for this section, which is 11.1, and you also have a Chapter 11 quiz. Good luck.